Okay, hello. I'm going to be going over chapter 11 from the textbook of Organic Chemistry by David Klein. I'm going to do some problems and go over most of the reactions we should know prior to this upcoming exam. And then I'm going to do questions increasing in difficulty until it encompasses everything that you should know after reading chapter 11. Okay, so first, before we start chapter 11, in the beginning of the chapter, there are these charts that it asks us to fill in because we should know which reagent is used in each transformation um, based off of both collectively chapter 8 and chapter 9. And so this diagram, you can do it in your own time, test it out and see if you, from your memory or from your understanding of chapter 8 and chapter 9, if you can fill out which reagents are needed. And it's helpful to have it's helpful to also test yourself first before you look over the solution set for it. And here's this as well. We can do every single one of these, or we could just like look at the solutions provided for these. I've already done this in my own time. I think I was lacking in like one or two of these newer reactions that we did not go over in class, but it is mentioned in the textbook. And like something from here that like tripped me up. Oh, this addition of both a halide and an alcohol, which we also did not go over in class, but it is mentioned in the textbook. Okay, so we'll reference this if we need to, but try your best not to. Okay, let's start with problem A from earlier on. Let me move this thing from earlier on in the chapter. First thing it teaches you is to check first for functional group changes in both location and functional group. In this case, we have an alkene that's becoming an alkyne. And so there is a functional group change, and then the location seems pretty much the same spot. Before you go into any of these problems, it's always just good practice to, whoa, that's really, really big. It's always good practice to number your carbons just to make sure you don't accidentally add an extra. And you don't have to follow the IUPAC naming for this. You're numbering for yourself. You're numbering for reference, right? And so we see we have 6 carbons in this one. And then we go ahead and number this one. Let's see, 4, 5. Oh, this is not 5. 5, 6. So 6 carbons to 6 carbons, great. So now we know it's just a functional group change, and so we can proceed. So with synthesis, the way the chapter teaches us, and I think is the ideal way of doing it, is retrosynthesis, which is like starting from the product and trying to figure out which starting material you need to have to get to that product. So in this case, we have an alkyne. And then from practice, you kind of can you remind yourself uh, which which reagents or which reactions will generate an alkyne for us. And I know there are 2 ways for myself, but for reference, let's just go to the table that we're going to be provided anyways for the test. Let's go through the products, right? This is this right here. Oopsies. This right here is the product list. And so let's go through this product list and find which one will give us an alkyne. Okay, there we go. We found one. This is our product. It's an alkyne, and it converts dihalide, geminal or vicinal, into an alkyne. So we know we're going to have some kind of dihalide. So we're going to go back here to our problem. And one that we know we can get to from an alkene is the vicinal dihalide. That's with the bromine added to either side of the double bond. So I'm already thinking ahead. I'm moving backwards, starting at the product, but I'm also keeping in mind what I want to get to. So that way, when there is 2 possible ways to get to a product, in my head, I know which one's more ideal to use based off of the starting material we want to get to eventually. So I know I want to get to an alkene, so I'm going to use a vicinal dihalide, and that would look like this. Okay, and to get to that, let's go back to our table preparation. Is excess of sodium amide over H2O. So H2O is the second step in it. So we're going to go ahead and do that. So we're going to do excess of sodium amine or amide. And then the second part of this reaction is adding H2O. Okay, and then we can double check it going in reverse. Going forward. We have the two bромines, and to get rid of them, we would use this strong base that would strip the anti-periplanar hydrogens. Okay, and then as each one strips, bromine acts as a leaving group twice. And if it's acting as a leaving group twice, we're going to get one double bond, we're going to get two double bonds. Great. So I'm going to delete my thought process behind that. This I have done already in a previous video in chapter 9. Feel free to review that video if you want to know like the exact mechanisms in more detail. Okay, so now we have this. We can almost like just directly now go to this vicinal dihalide by a reaction we should know from chapter 8, which is adding bromine across the double bond. If you want to reference a table, you sure can. Here it is, halogenation, X2, addition of two halogen atoms across a CC double bond. Great, and it's anti-addition. And so we know that's just going to be Br2, and usually the solvent we use is CClO4 as per that addition reaction chart. Okay, so this seems to be it for question A. Let me double check now and see if that's what I got in the answer key. Yep, okay. Okay, so I've already gone ahead and numbered our carbon skeleton for problem F. And we see here we're going from 5 carbons to 4 carbons, and we're also going from an alkyne to an aldehyde. Let me turn this off so you can hear me better. So yes, we're going from an alkyne to an aldehyde, and we're also going from 5 carbons to 4 carbons. But we start at our product for retrosynthesis, and we see here that we have an aldehyde. So how do we get an aldehyde? We go to our table, we look down their list for aldehydes, and we see we can get one through oxidative cleavage, but it looks here we can also get one through hydroboration. And I've already crossed that out because if we do hydroboration oxidation of an alkyne, it's of a terminal alkyne. So that means it would be adding an aldehyde to the end of that alkyne, and we would start with 5 carbons and end with 5 carbons. But that's not what we have. We have 5 carbons and then 4 carbons. So we know we're losing a carbon, and we know that can happen through cleavage, right? We have that double bond, and then we cleave it, and we keep the 1 carbon because it becomes an aldehyde. The other one also becomes an aldehyde, but in this case of this question, it's no longer a part of our molecule. It's no longer a part of our problem. So we're going to do oxidative cleavage, and that's of an alkene. Of an alkene. First step, second step. And it would look like this. Okay, and just confirm 1, 2, 3, 4, 5 carbons. Yep, that's what we have here. And then to get an alkene from an alkyne, we can just go straight. We already know this reaction, or we should. What will give us an alkene is H2 with Lindlar's catalyst. Okay, and those are the 2 steps for this synthesis. Let's go to the next one. This one also started numbering it. Let me get rid of this. So we have our cyclopentane, and then we have 1 additional carbon. So altogether we have our 6 carbons. This is our cyclopentane, and then we have 1, 2, 3 additional carbons. So we have 8 carbons. And so it looks like we're adding 2 carbons entirely. And so we know if there is a change in our carbon skeleton, there's alkylation likely happening because we're going from 6 carbons to 8 carbons. So that means we added something. And what do we the only way you can add is through an alkyne. So we know we're going to get to an alkyne at some point in this synthesis. So let's look at our product here. We have an alkene. How do we get to an alkene? From an alkyne. There we go. So let's do that. Okay, and then let's just confirm the same 3 carbons are still there. 1, 2, 3, and that happened through, because it's terminal, you can use either the H2 over Lindlar's catalyst, or you can use sodium metal over liquid ammonia. In this case, I just like to stick to what we've used in the past, and that's H2 over Lindlar's catalyst. Okay, and then going from this halide to an alkyne, we know we can do that by adding an alkanide ion. We add this entire thing plus the alkanide ion. Uh, And it seems in this case, because it's just two carbons, it's just the alkanide ion because there's a carbon here and a carbon here on either end. And this one has a negative charge and goes through, does a nucleophilic attack and replaces the chlorine. And so that's how we get from this to that to this. Okay, now let's do another problem. Let's do this one right here. So again, look at my numbers. I have 1, 2, 3, 4, 5, and it's going to 8. So I'm adding 3 carbons. So I know there's some kind of alkylation taking place here. I know we're going to have an alkyne at some point. So what gives us a cis alkene? And that's right, an alkyne will give us that with H2 over Lindlar's catalyst. Okay, and then to draw this, it's a little tricky. 1 to 2, 2 to 3, 3 to 4 stay straight because 4 to 5 is a triple bond. And then 5 to 6 stay straight, and then we have 6 to 7, 7 to 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Great, we've maintained all the carbons in this drawing. And then how do we make an alkyne? Well, there's 2 ways, right? We can make an alkyne from dihalide, right? But then that would like require an alkene before that, and then how would we get to this alkyne? So we have to keep our starting material in mind. So the other way we can do this is just by adding it through alkylation. Remember, we have the alkanide ion that we used earlier. We could have a 1, 2, 3, 4. We have our propyl here connected to a halide, and then we have our alkanide ion. And then the N here is 1, 2, then it's connected to 3, 4, 5. 3, 4, 5. So that would be 1, 2, 3, 4, 5 carbons. Okay, and we also have 1, 2, 3, 4, 5 carbons here. So it looks like we went from this to this. And the way to get to that is just by excess Na and H2 and H3. And then we add our propyl bromine. Okay. And then from that to this, we added it, we got this, and then from this to that is H2 Lindlar's catalyst. Neat. Okay. So let's do this one now. So here we're going from 9 carbons to 8 carbons. We're going from a dihalide to a carboxylic acid. But let's start at our product. So we have a carboxylic acid there. Let's go to our chart and see how do we create a carboxylic acid. Let's see. So it looks like we're going to have to use an alkyne. And it looks like it is this last reaction here, ozonolysis of alkynes, and it will give us carboxylic acid. So O3 and H2O. Okay. And then it looks like this was the middle of the alkyne. So then it looks like that this was like this, right? And let's check. We have 1, 2, and then we have 1, 2, 3. And so we have an extra carbon. That's okay because remember, we want to get to that 9 carbon. So we want to make sure that it has the 7, 8, 9. And in this case, it does the 7, 8, 9. Neat. So now how do we make an alkyne? And we can actually make an alkyne from, we can go look at the product table and it tells us from a dihalide. In this case, it's a vicinal dihalide. And we do that just by adding this can go straight from there to there by adding excess sodium nitrite. And water. Okay, and I think that's that for this question. Yeah, and so now let's go on. I think there's one more question. Let's do this one. So this one we have an alkene, but we're also ending with an alkene. Okay. Oh, look, there's a change to the carbon skeleton. We had 4 carbons, and now we have 6 carbons. So there was 2 carbons added. In my head, that's like ringing a bell. Alkylation, and which type? Seems like it just might just be the alkanide ion on its own because it has a carbon here and it has a carbon here. Those are 2 carbons. So at some point, it will get added into this. But nonetheless, how do we make a cis alkene from an alkyne? Okay, 1 to 2, 2 to 3, 3 to 4 is the triple bond, 4 to 5, 5 to 6. Okay, let's just number it so we can keep track of all of these carbons. Neat, okay. And then we see here that we have 4, we want to end with 4 carbons. So at some point, 1, 2, 3, 4, it looks like the cut is going to happen here because we still have our alkyne at the end and then we have the 4 carbons. So how do we do that? We would have 1, 2, an ethyl bromide plus our, oh, this is terrible, plus our alkanide ion with 4 to 5, 5 to 6 added. So this would give us the 1, 2, 3, 4 carbons, and this here is the 5, 6 that we ended at the end. And then to get from an alkene to this, there is an extra step here. We know to make an alkyne, we would need dihalide, and so we would need. We know we can make a vicinal dihalide, and so it would be like this with a bromine here and a bromine here. And we know to get from this alkene to this, we just add Br2. Remember, that's the addition reaction to alkene, adding X2 of something across a double bond. In this case, it's bromine. Okay, so we add it, and then let's go from front to end, from start to finish. Br2 CCl4 will give us the vicinal dihalide. Vicinal dihalide would give us an alkyne through excess sodium amide. And then in this case, we wouldn't need the water because it would stay as an alkanide ion, and we would just add this. And then to get from, and then after the addition, you would end up with this big chain with an alkyne in the middle. And then to get from this to this, we know it's H2 Lindlar's catalyst. Okie dokes. So this seems to be all the problems I have listed here. Again, I recommend doing these 2 problems on by yourself because this should be review, right? Try not to use any of these tables for reference for this, just so you can catch where you might be lacking, right? Okay. Good luck.